everyone. Yesterday we discussed about how can we find potential due to a point charge or due to an electric dipole. Today we are going to find out how can you find electric potential due to a system of charges. So for that, let us consider three charges: Q1, Q2 and Q3 placed like this, and we want to find potential, say at this point P. Say this point is at a distance R1 from Q1, R2 from Q2 and R3 from Q3. So if the potential at this point due to Q1 is V1, same at this point due to Q2 is V2, and due to Q3 is V3, then you can write the total potential as V1 plus V2 plus V3. Since potential is scalar quantity, you can just add them like this. So V1 will be formula due to point charge. Forget about the other charges now. So due to this charge Q1, the potential at P will be V1 equals to 1 by 4 pi epsilon naught Q1 by R1. Now in a similar way, the potential at P due to Q2 will be V2 equals to 1 by 4 pi epsilon naught Q2 by R2, and similarly V3 will be equals to, which is due to charge Q3 by RT. The total potential at V will be 1 by 4 pi epsilon naught, you can take it as out, Q1 by R1 to so this will be the potential. Now in general, they give you a system. For example, consider a square. Right? My drawing is not that good, but just consider for the moment that this is a square of side A, and there are charges. Say this is Q, this is minus 2Q, this is 3Q, and this is again say Q, and we have to find potential say in the middle of this square at point O. Just name them A, B, C, D. Now if the side is A, now O being the center, so they are equidistant from these charges. Okay, so let the distance is R. You can easily find the value of R in terms of A, which will be R equals to A by root. So total potential at O will be V equals to VA plus VB plus VC plus VD. So VA will be 1 by 4 pi epsilon naught Q, charge here is Q, divided by distance, which we assumed as R. Now VB, here is minus charge, so you can write plus 1 by 4 pi epsilon naught, this 2 minus 2Q, so minus 2Q divided by distance R. Now VC 1 by 4 pi epsilon naught, again Q by R, plus 1 by 4 pi epsilon naught due to VD 3Q by R. So 1 by 4 pi epsilon naught and 1 by R, we can take them common, so it will be like Q for this one minus 2Q plus Q plus 3Q, so it will be 1 by 4 pi epsilon naught minus 2Q and plus 2Q will cancel out, so 3Q by R, and if we put the value of R, we will get 1 by 4 pi epsilon naught 3 to Q by A. So this will be the potential at O due to the system of charges. So you see, we just add them in algebraic sum. Now let us discuss about equipotential surface. Now from the word equipotential surface, you can easily say that it is such a surface on which the potential remains the same. Okay, now we have to draw equipotential surfaces for different types of system. Now for a point charge, say here is a plus q. The potential due to a point charge at any distance r is v equals to 1 by 4 pi epsilon naught q by r. So you see it only depends on small r, the distance from it. So you can easily say that the at a distance r, if we draw a sphere, now on any point on the sphere the potential will be same, since it only depends on r. So for a point charge, this is case 1 point charge. The equipotential surfaces are concentric spheres. Now you know the electric field due to a point charge is radially outward. So this is electric field direction, and this is the equipotential surface sphere. So in general, in case of any type of system, whether it is a point charge or multiple charges, okay, the electric field and the equipotential surfaces are always perpendicular to each other. We'll prove it in later. Now consider uniform electric field. Now I already told you that the uniform electric field is represented as equispaced parallel lines. Okay. In case of such field, the equipotential surfaces look like plane. This is the plane parallel to each other. You can draw as many number of planes. So these are the equipotential surface on a given surface. Suppose on this plane, the potential will remain same. Now consider a system of two equal positive charges or maybe negative charges, but same, either both positive or both negative. Now in this case, the equipotential surfaces will be spheres but not concentric. They look like something like this. Similarly on this side, if you see here, the spheres have more spacing than in this side, and also as a whole you will get less. It's like this in case of both positive or both negative. Now in case of a dipole, we already know that a plane in the perpendicular bisector, the potential is 0 throughout this plane. So this is also equipotential surface. Now along with that, we will still have not concentric spheres like this, but in that case the spacing here will be a little bit more than on this side. So this will be something like equipotential surface. This one, this plane, these are all equipotential surface for a dipole. This is for a dipole. Now these equipotential surfaces have some interesting properties. For example, the electric field and equipotential surfaces are perpendicular to each other. Already said that. Secondly, these equipotential surfaces do not cross each other. If they crossed, then at that point there would be two directions of electric field. So equipotential surfaces do not intersect each other. Now third point is, since the potential throughout the surface is same, we do not need to do any work to move a charge along this surface. So these are some of the properties of equipotential surfaces. Now let us find out how electric field and potential difference are related to each other. Now for that, we will consider two equipotential surfaces separated by a small distance. So consider two equipotential surfaces and 2 points on them. Say the electric field is in this direction from left to right side. Okay, so it is obvious that the potential at this point will be more than that, since we will have to do more work in bringing a unit positive charge from here to here. So say potential at this point is V, and here it is a V plus dV, and the distance between the two planes are say dl. So suppose we bring a unit positive charge from this point to this point. So the work done will be the difference between the potentials. So we can write, now if you see the electric field is in this direction and we are moving it in this direction, so they are opposite to each other. So the work done will be minus EDL, and the potential change in potential final minus initial, sorry V. So we can write minus EDL equals to dV, or E equals to minus dV. So this is the relation between electric field and potential. Now let us find out potential energy, electrical potential energy of a system. Okay, suppose for that we consider a system of three charges. So by definition we already know that we have to bring the charges from infinity to a given point. So suppose there is no charge. Okay, as there is no charge, there is no electric field. So to bring the first charge from infinity to this point, we will have to do no work against the electric field. So in bringing the first charge, say Q1, the work done is 0 against the electric field. Now suppose we bring the second charge at this point, and the distance from this is say R12. Now when we brought the charge Q1, there was no charges around, so it did not experience any electric force, so the work done is 0. Now once we placed this charge, because of this charge there is electric field. So now if we want to bring another charge Q2, we will have to do external work, and that external work is W equals to, you already know, potential due to this charge at this point multiplied by its charge. W equals to VQ formula, so that is V1. V1 is the potential at this point due to this charge multiplied this charge Q2. So in bringing this charge from infinity to this point R12, the work done is W equals to potential due to this charge at this point multiplied by the charge of this charge. Okay, so this is a W1, so this is the work done in bringing this charge. So now if we bring another charge, say here Q3, now at this point there will be electric field because of this one as well as this one. So in bringing this charge, the work done will be, say, potential due to this and potential due to this. We have to consider the both. Okay, so first we bring this charge, no work done. We bring this charge, only work done against because of the potential of this charge. Now we bring the third one, the work done will be because of the potential of this one as well as of this one. So the work done in bringing this charge only, W2 will be equals to, say, V1 prime because of this distance into Q3 plus, say, this is V2 prime into Q3. So the total work done will be W equals to W1 plus W2. So to assemble this system of three charges, we need to do this amount of work. Now V1 is potential at this point due to this charge, so we can write, this is first just put the value V1 Q2 plus W2 V1 prime Q3 V2 prime Q3. Now we'll just put the values of V1 prime and V2 prime. Now V1 is potential at this point due to Q1, which will be 1 by 4 pi epsilon naught potential Q1 divided by distance Q1 R12, and this is always there Q2. Now say this distance is R13 and this distance is R23. So if you just put the value V1 prime means potential at this point because of Q1. So that will be 1 by 4 pi epsilon naught q1 by r13 into q3 plus 1 by 4 pi epsilon naught. The v2 prime is potential at q3 because of q2. So this will be q2 by r23 into q3. So if we take common 1 by 4 pi epsilon naught, this will be q1 q2 by r12 plus q1 q3 by r13. This is q2 q3 by r23. So this is the total work done that we have to do. So this amount of work done will be restored in this system. The potential energy of the system will be same. This is also the potential energy of the system. Now in question, they generally ask about the equilibrium of the system. Now a system of charges will be in equilibrium if the total electrical potential energy of the system becomes 0. So for a system to be in equilibrium, the total potential energy should be 0. Now again in a system, if they ask to that a charge to be in equilibrium, if the system is to be in equilibrium, total potential energy has to be 0. If a charge has to be in equilibrium, then the net force should be 0. For a, just remember the difference, charge to be in